Okay, good evening. So nice to see you again. And we will continue our yeah lectures for this course. So today we will mainly talk about carbon peaking, carbon neutrality, and how to design energy efficient buildings. So firstly, let's have a look. Let's understand when we talk about carbon emissions. So let's know more about where the carbon emissions from our society, from our earth, and also sure from our buildings. Okay, what are carbon emissions? Carbon emissions generally refer to the release of carbon containing gases. Primarily, is carbon dioxide into the atmosphere. These emissions usually are the byproduct of some natural processes, and especially because of the human activities, such as the burning of the fossil fuels and deforestation and certain industrial processes. So let's have a look at the fossil fuels. So what is fossil fuel? So fossil fuel is a flammable carbon compound or hydrocarbon containing material formed naturally in the Earth's crust from the buried remains of prehistoric plants, animals, and macro planktons. So here is mentioned because the the emissions of carbon mainly from due to the combustion of fossil fuels. So we can see the fossil fuel mainly including like coal, petroleum, and natural gas. So we can see they are mainly with the carbon, hydrogen, and oxygen. And then we want to know more about carbon, then we know, but for carbon itself. So here is also mentioned, is here is carbon compound, okay, or hydrocarbon containing materials. So we can see there's carbon and also hydrogen, okay. And then we look at carbon. Okay, carbon, in fact, is a chemical element. And also, we understand its freezing point and its boiling point. Okay, so, and atmospheric conditions. Okay, they exist in solid state. Carbon makes up about 0.025% of our Earth's crust. And these are some common, graphenes and diamond. They are two different allotropes of carbon. And softest and hardest. And sure, carbon is also very hot element because they have different allotropes of carbon, like fullerene and carbon quantum dots. Also, all of them are different allotropes of carbon. So carbon, in fact, different allotrope of carbon becomes, I think it's very popular star, okay, in material science now. Then we look at the fossil fuels. That is because we can see because fossil fuels are different carbon compounds. So with carbon, that is because, okay, carbon can form very long chains of interacting carbon bonds. And this is the property that is called catenation. And also carbon and carbon bonds are very strong and stable. And through catenation, the carbon forms a countless number of compounds, and also a similar to be made for hydrogen, because most organic compounds contain hydrogen as well. So that is the reason when we talk about so for animals, plants, so they always have the element of carbon. And sure, these are called organic carbon compounds. And methane is the simplest possible organic compound. So that's when we look at town gas, okay? So this is also the main composition of the town gas in Hong Kong is the methane, okay? Is methane. And sure, for other fuels, so this is the simplest one. So the including carbon, hydrogen, and oxygen, because they can also establish strong bonds and with oxygen and nitrogen and hydrogen as well. And this is organic compound, carbon compounds. So then when we talk about biomass, okay, biomass. Okay, so we know biomass is also considered as a renewable energy. Okay, as a renewable energy, biomass energy. That's the same. Okay, it's the through different combustion or different processes. Okay, our biomass such as plants. Okay, into biofuels. They also will release carbon, okay, carbon emissions. Then let's know more about in our daily life. So the carbon emissions, that is mainly carbon dioxide. Okay, the most most popular one that is including inorganic compounds, inorganic one. Okay, sure. Also, we have to be careful of carbon monoxide. Okay, so we know some people, okay, in a confined spaces. Okay, so they're using carbon, okay, to end their life, suicide. So that is in a confined space with insufficient oxygen, the combustion, the byproduct will be carbon monoxide, okay, which is dangerous, okay. And it is formed by incomplete combustion, okay. So carbon monoxide. And then for the carbon emissions is the inorganic compounds of carbon. So carbon monoxide, carbon dioxide, in fact, is a colorless, odorless gas, but it's very vital to the life on Earth because, okay, and it can be also considered as a trace gas comprising 0.039% of our atmosphere. So why carbon dioxide, is unfriendly to global warming, to the energy balance of our Earth, but it's vital to the life on Earth. That is because carbon dioxide is used by plants during photosynthesis, okay, and to produce, okay, in fact, to make sugars, which can be either be consumed or used as a raw material to produce other organic compounds needed for plant growth. So in this way, okay, in organic carbon compounds into organic one, so which can be considered as consumed, okay, by the plants and also by animals and by predators. Okay, okay. Then for the life cycle, for the life on the earth. And then after understanding carbon and carbon emissions, and we also know the property of carbon dioxide, and where carbon emissions from. Then when we look at for our buildings, the sources of carbon emissions in buildings, that's mainly including the operational emissions. So this including emissions generated during the use phase of our building, primarily from energy consumption for heating, cooling, ventilation, lighting, and powering appliances, etc. And the majority of operational emissions are due to the combustion of fossil fuels in power plants, okay? In power plants that supply electricity to buildings. Sure, and also on-site fuel direct use as well, okay? For cooking, for producing hot water, for shower, and other uses. And then there's carbon emissions in our buildings due to the embodied emissions. That means these emissions associated with the extraction, manufacturing, transportation, and installation of building materials, as well as construction activities. So embodied emissions also include those from maintenance, renovation, and eventually demolition. So embodied emissions, that's mainly for the construction, okay, construction phase, so the materials, okay, the building materials for their manufacturing, their transportation, and on-site construction, and sure, so and also for those building materials for their maintenance, renovation, and also eventually demolition during their life cycle. So generally, for the Earth, our buildings are significant contributors to global carbon emissions, accounting for around 30 to 40% of total energy use, and also similar figures as the associated carbon dioxide emissions. These emissions from direct and indirect sources related to building construction, operation, and maintenance. So look at why building consumes, so for this world, over 30 to 40% of energy. That is because, okay, in fact, it's very famous, okay? You know, so in Africa, some people live in mud huts. They don't need artificial lighting. They don't have air conditioning. So sure, the buildings consume almost no, okay, no energy, okay, no no electricity. And even in China, we have cliff homes previously. That is because between the outdoor environment and the built environment, and the cliff, the mountains as the envelope, okay, as to separate outdoor environment, indoor environment. So for the African mud huts, they are using, okay, mud, okay, to separate outdoor environment and indoor environment to provide a better indoor built environment. Then later, yeah, sure, if you want to experience, we still have cave hotel in Turkey. So, so to experience, as the mountains, as the mountains, the cliff, okay, the stone, okay, the natural as our building envelope. And that is now you see, so especially like for Hong Kong, we have high-rise buildings. So we need, okay, artificial lighting. We need electricity for vertical transportation, for ventilation, for air conditioning. And and for our electrical appliances. So that's the reason for with the advancement, modernization, urbanization of uh, our world. So we look at the fingers. So buildings, are the main contributors to electricity consumption. Is the biggest energy user and sure also the main contributor to carbon emissions. So that's the finger for Hong Kong. And then we can see for mainland China, we have looked at the fingers. Look at the finger several years ago. In fact, our buildings in their whole life cycle account for around 41.3% of total national carbon emissions. Okay, so this building energy consumptions and with its associated greenhouse gas emissions, mainly from for the production and transport of the building materials and building construction and building operation and maintenance and also building demolition. If you look at their breakdown, you can see. So around 51% for the emissions. And for that emissions for building materials, is around 28% carbon emissions is to produce and to transport those building materials. And sure, during operation, it's still operational emission, around 22% contributes to 22% of national carbon emissions. Sure, for the construction process and the demolition process, the eventual demolition process is contributes to around 1% of national carbon emissions. And if we look into the details, for building materials, the main contributor is to produce and to transport the steel and the iron, so which are the main building materials for modern high-rise buildings. And sure, the second comes the cement, and also aluminum also comes third. That's mainly like for our window frames and other purposes, and even for some metal structure buildings. For the operational, sure. In fact, for China, residential sector is the main contributor for the operation. And then comes the commercial sector. And for the rural side, although before we have the large population, but it still contributes to less due to their, I think a lower level of energy demand and energy use. These are the carbon emissions from the building sector for mainland China. So what about Hong Kong? Following the previous slide, we can see, in fact, our buildings account for about 90% of electricity consumption and around 60% of carbon emissions. Then for Hong Kong, so with the commitment to carbon neutrality, so we are looking, we are trying to, so from the supply side, we have our target, to achieve net zero electricity generation in 2050. So for the plan is in 2033, no coal for electricity generation. And then around 60 to 70% zero carbon energy. So that's mainly from solar energy, wind power, nuclear. I think that's mainly from nuclear power. Nuclear power. And then we expect the share. I don't think we can achieve it. 7.3 to 10%. That is because, the proposal, the plan to develop offshore wind farms, about it, were given up. So I don't think this figure we can achieve, but I think that's mainly we will rely on nuclear power, However, we have the target. So for our Hong Kong's climate action plan, so is in 2050, we can we can achieve the net zero electricity generation. And that's for supply side. For demand side, sure, we always promote energy saving and green buildings. So then we have the plan. So for different sectors, so to reduce their energy use. In 2035, so the energy use reduction is 15% to 20% for commercial buildings and 10 to 15% for residential building. Should be the benchmark with the data in 2015. And sure, so for our in 2050, so with the more energy saving reduction, Then after understanding, so firstly we understand the carbon emissions, carbon, organic compounds, and also carbon emissions in buildings, and in Hong Kong, in China, and also for this world. Now let's have a look at the carbon cycle and the greenhouse gases. So, in fact, we have to understand the carbon cycle for us to better understand why we have the commitment to carbon neutrality. So the carbon cycle is a natural process in which carbon moves between the atmosphere, oceans, and soil and living organisms. Plants absorb carbon dioxide during photosynthesis, during photosynthesis, converting it into oxygen and organic matter. So they can be used directly to produce sugar. So the organic matter can be used by themselves and sure, provide food for animals. And animals and humans release carbon dioxide back into the atmosphere through the respiration. So we are breathing out carbon dioxide. Decomposition of dead organisms and volcanic activity also contribute to natural carbon emissions. Decomposition of dead organism and also volcanic activities will also contribute to the natural carbon emissions. So, however, we have more focus on the red one, the red one due to the human activities. The red one are human contributions. We look at here. Is due to the atmospheric carbon net annual increase is causing, so the concentration level increase, and due to the combustion of fossil fuels and inappropriate of land use changes, also causing the contributes to the emissions of carbon emissions. And so when we talk about carbon emissions, we talk about merely the carbon in the atmosphere, okay? So carbon in the atmosphere exists in two main forms, including carbon dioxide and methane. Both of these gases absorb and retain heat in the atmosphere and are partially responsible for the greenhouse gases. Later, we will know more about greenhouse gases. What are the greenhouse gases? Methane, this is methane. Methane. The simplest organic carbon compound. Methane produces a larger greenhouse gas effect, but it exists in relatively lower concentration levels. So, and also more short-lived than carbon dioxide. So it can easily, connect with the other elements. But carbon dioxide relatively stable. And therefore, carbon dioxide contributes more to the global greenhouse gas effect than the methane. So that's for the carbon. So we look at the figures, sure. So carbon dioxide concentrations over the last 800,000 years as measured from ice increases, especially, in the past, I think 200 years. So due to after the Industrial Revolution. So, and look at the updated figure. That's mainly due to, so we experience Industrial Revolution 1, the first Industrial Revolution. So I think it's around in 18th or 19th century. So that is mainly, we can convert thermal energy into mechanical energy. The first industrial revolution is mainly thermal. Through the combustion of fossil fuels, the thermal energy, can be converted to mechanical energy. It's very useful. Because the combustion of fossil fuel, the invention of a turbine, of the piston, which the mechanical energy can run the wheels, can run the cars, can run our ships and trains, and even weapons machine. So this is the first industrial revolution. So mainly we experience from thermal energy, mechanical energy is very useful because it can run the wheels of our car, our train. And then the second industrial revolution, is around 120 years ago in early 20th century. So it's electrification. It's over 100 years ago. There's the invention of a power generator to produce electricity. We found electricity is very useful. And nowadays we know, and this is the invention of electricity. So the first industrial revolution is mechanical, and I think it's how to produce and make use of mechanical energy. And second revolution, I think is electrical energy, okay? So to power plants to produce electricity. And then, after that, the invention of a solar cell, we observe power, okay, solar cell and wind turbine for power generation, etc. And even air conditioning, okay? So around 100 years ago, because we can see that electricity can drive, can drive the heat engines, the reverse heat engines, to remove heat from the low temperature space to the high temperature space. And what about the current fingers? So look at now, I think the fingers is around 420 ppm around atmospheric carbon dioxide. Okay, so it's the finger. I think it's it's very important. So if you are building engineer, so for the design of your air conditioning system, you need to introduce outdoor fresh air into the indoor environment to remove the carbon dioxide and provide fresh air. Then the calculation we have to is very important. So the intake loofah location to make sure. So the fresh air with relatively lower ppm, okay, so carbon dioxide concentration levels. Then, in fact, after understanding the carbon cycle and also understanding the carbon emissions, then let's see how carbon emissions in the atmosphere will affect. Okay, it's very important to the to the life on Earth, and even why we talk a lot about carbon peaking, carbon emission. That is because we think the energy is the driver of climate, and in fact, this is a Fourier. Okay, he is a mathematician, and he calculated the Earth's temperature. Then he found his calculation and the actual temperature of our Earth is different. Why? That is because the atmosphere, because we have atmosphere. Okay, so he kept because the atmosphere you cannot see it. We think it's just okay, transparent. It's nothing. But the calculation of the Earth's temperature is different. The theoretical one is negative value, and the actual one is around 15 degrees Celsius. That is because the existence of the atmosphere. When we look at the atmosphere, there is the different composition of the atmosphere. They will affect the solar energy, which can penetrate through it to the Earth's surface, and also the atmosphere, especially those greenhouse gases, will trap the heat, leaving the Earth. So look at the first greenhouse gases is the water vapor. Water vapor, in fact, is the strongest greenhouse gases, and the concentration of this gas is largely controlled by the temperature of the atmosphere. Water vapor is the strongest greenhouse gas. Okay, and then carbon dioxide, in fact, is the comes as the second important greenhouse gases. One reason compared with the methane is it has a long lifetime in Earth's atmosphere. Okay, and later we will let you know the carbon dioxide. So especially strongly absorb energy with a wavelength of 15 micrometer. So later, I think we also have a tutorial problem on that one. So to understand how carbon dioxide will absorb heat, leaving the Earth. This makes carbon dioxide a good absorber of wavelengths falling in the infrared radiation regions of the spectrum. And methane is 30 times stronger than carbon dioxide as absorber of infrared radiation. However, as previously we mentioned, although it's a stronger absorber of infrared radiation, but it has relatively lower concentration levels, and also it's can be easily react with others. Okay, so with a shorter lifetime. And the third, okay, water vapor, so greenhouse gases. The first one, second one, and also the ozone is, I think here is the third one. The ozone is also a relatively minor greenhouse gases because it is found in relatively low concentration in the troposphere. And there's others, so including halocarbons. Okay, the halocarbons are composed of carbon, chlorine, fluorine, and hydrogen, etc. So now we understand. So although we mainly talk about carbon dioxide, but sometimes we have to still alert, okay, with the water vapor and methane and also the halocarbons, because halocarbons usually, okay, released from our air conditioning system, refrigeration system, the refrigerants, okay, our refrigerants usually are halocarbons. And also for the insulation materials, and also for some, I think it's cleaning agents also will release halocarbons, okay, the halocarbons. And then, in fact, although Floria observed did the calculation and observed we have the atmosphere, their different composition, then we understand the greenhouse gases, okay? Water vapor and carbon dioxide are the two main greenhouse gases. They can absorb radiation with a wavelength in the range of 4 to 80 micrometer, but it's except 8 to 13 micrometer. That is called atmospheric window. It opens, our atmosphere opens a window. If any thermal radiation, their spectrum, okay, lies in between 8 to 13 micrometer, it's open, the heat can leave it. And the ozone can absorb wavelengths between 9 to 10 micrometer. Okay, that is so we can see, but this figure is not the updated one because we can see now the carbon dioxide in the atmosphere is over this figure, is around 420 ppm already. And so we see the methane and ozone and halocarbons, etc. So here we understand, in fact, so we can see carbon dioxide, black means it will absorb heat, outgoing infrared light radiation from the Earth. And water vapor is the first greenhouse gases. See, we can see is the black region is the all the infrared radiation will be blocked by the water vapor in the atmosphere. And for oxygen and ozone, okay, they absorb in this region, okay. However, basically, it opens a window, okay. For the total one, there's a window. So that means if your thermal radiation is with a wavelength in 8 to 13 micrometer, the atmosphere cannot absorb the heat and will let you passing through. So now we understand due to the concentration, the increase of the concentration levels of water vapor and green and carbon dioxide, more heat, okay, outgoing infrared radiation will be trapped by the greenhouse gases, so which causing the Earth's energy imbalance. So that's causing the global warming, the temperature increase of the Earth. So then we talk about since the Industrial Revolution, okay, there's a sharp increase of the greenhouse gas concentration levels in the atmosphere. Now we talk about carbon. Because we think regarding the water cycle, it's difficult to control the water vapor. So we talk about carbon. So, but not only I think it's carbon dioxide, but also methane and halocarbons as well. So we can see this is due to since the Industrial Revolution and the carbon emissions, the increase of carbon emissions. So we can also see obvious sharp increase of temperature of our Earth, okay? So it's a change from pre-industrial levels with a sharp increase, especially in the past, I think since 1970, okay? With the fast development and urbanization and industrialization, okay, in 1970s. So we can see here is a critical point. Because when I was little, so we don't have electricity, okay, for most people. We even don't have electricity. So China, I think, developed fast since 1990s, okay, 1990s. So before that, I think most regions, this is only the fast development for European countries, for United States. But since 1970s, even Hong Kong, even for some regions, so experienced rapid development, urbanization, industrialization. So therefore, okay, since 1970s, there is a sharp increase of our global mean temperature. Okay, sure, that's due to the industrial, the human activities causing the sharp increasing of the carbon emissions. So this is global average temperatures increases sharply. So since 1970s, okay? And maybe you think I don't care because you see the temperature maybe increased now is only 1 degree Celsius. It's okay. So we enjoy the sunshine if it's hot outside, but we have air conditioning. So very comfort. So over the year, we can keep the built environment at constant temperature. But a tiny increase of the temperature will causing other consequences. For example, you can see the one is the melting of the Arctic ice, sea ice. With the continuous okay, melting of the Arctic sea ice with the sea level rises. So we will experience more vanishing lands and cities. So I think 1 or 2 years ago, there are many news about Hong Kong. Even PolyU, even Shatian will be underwater. Okay, so for the projection after 50 years, 70 years, without the carbon commitment to carbon neutrality. So I think it's half region of Kowloon side will be under the sea levels. And so even not only temperature increases, but our climate change, global warming, triggered extreme weathers, the high frequent occurrence of extreme waves, extreme weathers, including heat waves, droughts, wildfires, and floods. That's due to the global warming. Global warming triggered lots of consequences, including extreme weathers, not only the melting of Arctic sea ice, but also extreme weathers such as heat waves, droughts, wildfires, and floods. So one example even is every 1 degree Celsius increase in temperature, the atmosphere can hold about 7% more moisture. Okay? This is the reason why there's many places with heavy rains and floods. Okay? Because one temperature increase, so the trees will evaporize, and the ocean, the water will evaporize, and then the atmosphere will hold about 7% more moisture. And we still remember water vapor is the first greenhouse gas, okay? The first greenhouse gas. And sure, in the last few years, even I have a friend, so now he moved from America to Hong Kong, so working in Hong Kong University. So this Sunday, so we were in Nanjing. Okay, this weekend I was in Nanjing for a conference. So when he presented, he said, "Oh, I came to Hong Kong in 2022. Every year, I experienced hottest year. Okay, since 2023. So he presented in 2022 the news about the hottest July, hottest August. Then 23 again hottest. And later I will show you even 2024, 35 temperature records different. And I think sure last year is the still hottest. Even now, still very hot, warm, okay? So we enjoyed the warmest Christmas holiday, okay? I think it's I think for girls it's good because they can wear sexy clothes. Okay, it's not very cold, and not only the recorded highest temperature, hottest year, hottest May, hottest June, hottest July, hottest year. But we can see, in fact, it also trigger the extreme weathers, including heat waves. The air, the mass, what is it's in the recent 2 years, heat dome is also a popular word you will read from the news about climate change. And because the warm air, a mass of warm air builds up in still and dry summer conditions, and with the high pressure in the atmosphere pushes the warm air down, and the air is compressed and gets even hotter. Okay, so for one regions, there's a hot heat dome effect, and I think it's warm up the further high we experience further hot local temperatures. And so believe not only we see the global temperatures in the past 100 years increases by 1 degree, we don't care. So we think about, because we have air conditioning, we have refrigeration. But the truth is, we can see the global warming, the temperature increases will trigger other consequences. And a small shift makes a very big difference. That's the reason I think everyone here we have consider this seriously and see how we can help. So this is the story I'm telling. So not only the highest recorded air temperature, I think this is a high recorded air temperature. This is the news. I think I don't see the Hong Kong breaks 35 temperature records in 2024, hottest year city's history. And sure, last year is still the hottest compared to 2023. So last year, you can see, I think it's Phoenix, the city in America experienced its hottest air temperature is over 47.8 degrees Celsius. Even there are more news about, the European heat wave caused the deaths, and causing the failure of power utilities. And even in China, it's reported, the surface temperature. Can you see the finger? So it's in May. And for China, the surface temperature is over 70 degrees Celsius. Not only air temperature, but the surface temperature. So I think in the coming few lectures, maybe we can discuss more about why air temperature is 30 to 40, why surface temperature can be over 70, 80%. Even I think, I remember this last summer, I was in Xi'an for a conference in late August. You know, the air temperature is around 40, 37. We couldn't walk outside because the surface temperature may be over 80 degrees Celsius. It's like being steamed. I think the steam, how to say, the feeling. So we couldn't walk outside for more than 3 or 5 minutes. It's really, really hot. And even the heat dome effect causing our cities to be even hotter centers. So then we talk about carbon neutrality, carbon peaking. So what is carbon peaking? Carbon peaking is to the point in time when carbon dioxide emissions stop growing and peak. So what about Hong Kong? Hong Kong has already reached our carbon peaking in 2015, And around 50% have reached a carbon peak, accounting for about 36% of global carbon emissions. So what about China? So it will reach the carbon pledged to peak carbon emissions by 2013. So then what about carbon neutrality commitment? So we know, I don't know, the commitment to achieve carbon neutrality of London is 2030, and Hong Kong is before. That's for most developed countries and regions and cities, before 2015. And China, China is here, 2060. So China pledged to achieve carbon neutrality. And so there are many different strategies. to achieve carbon neutrality, not only to reduce carbon emissions, but there's other technologies like carbon capture, carbon capture and storage technology. Okay, we have different strategies even to achieve carbon neutrality. So for buildings, for our building sectors, sure, we mainly reduce the carbon emissions, but we do have other technologies to capture the carbon, to store it, okay, to use to utilize them. Even I think we have researchers even to store the carbon in the cements, in the building materials, okay, for storage. So there's a carbon capture technologies and a storage technology. We work together. We try to reduce carbon emissions. We scientists also developing new technologies to capture and to store the carbons. Okay, so then finally we can achieve the target of carbon neutrality. Hong Kong, our commitment is 2050, and China is 2030%. Then, if you have interest, in fact, you can also download and read the Hong Kong's Climate Action Plan. So this is from that. So we reached the carbon peak in 2014, and we try to reduce the carbon emissions. And sure, we also develop other strategies, okay, to trade carbon, different strategies to achieve carbon neutrality in 2050. So now we understand for building sector, that's merely we should merely reduce the carbon emissions. And sure, together we can also in our buildings we can also building materials store the captured carbon, and also we using different solvents to absorb carbon dioxide for carbon capture and storage. And sure, so one another very important is to reduce building energy use and reduce carbon emissions. So for our buildings, sure, because it has a whole life of carbon emissions of our buildings. So we have to, from the design stage to operation stage, we also have to implement those ideas into our buildings. So including some energy efficiency component products and into energy saving systems. And including, we have to consider our single buildings, sure, also building clusters, and to achieve, low energy cities. And for buildings, we have also, with the advancement of different technologies, we also consider if some technologies, some system can be empowered by AI. And also, nowadays, due to the diverse demand side and the supply side, we have to consider the flexibility of our energy. Flexible energy use for the cross-scale source grid load storage in cities and buildings. So here mentioned, so we have to consider the cross-scale source, the supply side, the grid, and the demand side load, and also the storage, to achieve a flexible energy use. And as I mentioned, due to the frequent occurrence of extreme weathers, we also have to rethink about if our buildings will, to provide energy resilience, of our buildings, especially facing the extreme weathers and other uncertainties. So look at the details. I think I just summarize. So simply we can consider, so from at the design stage, okay, for the design stage, this is for design stage. For design stage, because for me, I immediately will introduce the design stage, the design, and the other collector will mainly mention about the flexible energy use and energy resilience, and how to implement AI into our building energy management. Okay, so for the design, is we can see is for is active design and passive design. So for active design, in fact, is to design our building energy systems, okay, to create a comfort, safe, resilient, okay, built environment. And the passive design is try to make use of the ambient energy sources. Okay, I think later, we will know more about what are the ambient energy sources we can use, okay, for our buildings, for our building cluster, and for our cities. So this is, in fact, passive design is very with a very long history. So, for example, so in Middle East, we have ancient air conditioning system. So look at underground because the temperature is lower. So the hot air will be cooled down by the underground water. Okay, it's called QNET. Okay, QNET. So one is there's a conduction heat transfer. Then there is convection heat transfer, and also there is water vaporization. You know, because it is dry, then the water vaporize, and this vaporization process will cool down the surrounding. So the warm, hot, and dry air will be cooled down and also humidified, and it will be heated. Then heated air, warm air is light. So through the chimney effect, okay, there's a so to circulate the natural air ventilation, okay. And sure, in China, we have the buildings, okay, they choose the thermal insulation materials such as bamboo, okay, to reduce the heat transfer between outdoor environment and indoor environment, okay, and even for the Forbidden City, the palaces, you see the design. So for the tiling, the roofing system, the tiles, the position, they consider the sun position. So this is winter, there's daylight will be introduced into the interior space, okay, and also to warm the building. But in summer times, okay, so there's no direct sunlight enters the buildings. So they make use of the architecture design, okay, to make use of the natural resources such as solar energy. And for the roofing system, okay, they have the air gap, okay, to prevent the conduction heat transfer, the heat loss through the roof, okay. So these are the, and even, okay, they are using the light pens to reflect sunlight, so to cool down our buildings, to cool down the buildings. So these are the passive design in ancient times, okay, to make use of the ambient energy resources to provide a comfort built environment. So Then I would like to talk about, let you know more about the natural energy resources, have a full picture if we have making full use of it or not. So look at our sun. In fact, our sun, the total output energy through its luminosity is I don't know what's the units. Okay, anyway, there's a huge power from the sun in the solar system. Okay, how much our Earth has received? This is our Earth is receiving 174 petawatts. Okay, annually. This is a watt. This is a rate. Okay. And we can see at other important figures is at Earth's orbits. So we see that for different seasons, the distance between the Sun and the Earth is different. However, for the solar constant, we consider with the average distance from the Sun, the energy flux is 1,367 watt per square meter. This is the solar flux approaching the top of our atmosphere. Okay, it's a constant. And for what about the average received solar energy on the Earth is annually, the average figure is 340 watt per square meter. Do you think we make full good use of solar energy? I think definitely is not, because now we are experiencing the global warming. But our plants making good use of the solar energy. They can even trace the sun, okay? Try to receive, but make better use of the solar energy. Then what about the other resources we can use is the cold universe. Our universe is cold. So we can observe them, okay, in nature. The answer is yes. So look at night, in the morning, we will observe dew. So on the plant leaves and even the frost. Okay, this is due to the leaves radiate thermal heat into the space, especially during a clear night. So the leaf temperature can be lower than the dew point temperature and even the freezing point. So the plants, okay, they know from the feature, we know this phenomenon is because of the cold universe. The universe is cold. It has a heat transfer between the plant and the universe and the space beyond our buildings, beyond our Earth. Okay, then we look at the finger. In fact, the Earth can radiate heat just like the plant into the cold universe. How cold it is. The universe, the lowest temperature of our universe is minus 270 degrees Celsius. Okay, it's only 3 Kelvin degree. So maybe you are curious about what's the cooling capacity through the thermal radiation. Okay, cooling capacity is 220 megawatts. Okay, there's a large potential, and its cooling density is 150 watt per square meter. Do you think we make good use of this, the coldness of our space? Definitely the answer is not, because there's a global warming, although we have a free cooling source. Luckily, even I'm working on this to make use of the cold universe as another natural source. I think in the future we may have the opportunity to share more. Then what we can use is wind. because we talk about natural ventilation. So sure, before we know more about natural ventilation, we need to know what is wind. Wind is air movement. The air is air movement. So the air movement due to temperature difference or pressure difference. But we cannot see it because we cannot see air. It's like Floria, because he did the calculation, he got the bears between the theoretical and so, but we can see it. So then we want to know if the wind energy can be make utilized, not only for wind power generation, but make use of the wind, the air movement to remove heat, to remove pollutants generated by urban cities. The answer is yes, it's urban ventilation. Should we talk about wall effect? So if you are design urban planner, you know this well. The prevailing wind to let the wind, the air movement to remove the heat, to remove the pollutants. So urban ventilation is very good way, okay, to cool down our buildings, our cities, okay, because when there is wind, convection heat transfer is always dominant. And then we see, so our urban planner will design the building layouts and the planning, considering the wind direction. So to let our cities breathe freely, okay? Don't trap pollutants and heat, okay? And what about for our buildings? In fact, we learn from the ants, the termites. So look at the termites, okay? This is its nest, okay? It's very, very complicated with thousands of channels, okay? So they make use of, if there's a sunshine, is heated, the air becomes light. Then the air will from the cold side to the warm side. Okay, so with the driven by the solar energy to achieve natural ventilation from all direction of channels. Sure, we successfully learn from it. So because we consider the prevailing, the windward side and the leeward side, so to introduce a natural air. And sure, if it's warmed, it's heated, then becomes light. Warm air is light, okay, to get the application. So another public concept we can see is very clear is cold air in and is heated, warm due to the internal heat load, and warm air becomes light. So it's called stack effect. Sure, can also see the ventilator, okay, to speed up so the natural ventilation in our building. So after understanding better about the wind, so I wish in the future you can make a good use of the wind, okay, for our building design. Another is the water. You may be curious about, can we make use of water for energy efficiency? The answer is yes, because we can see the dynamic water cycle, okay, holds a large amount of energy, approximately 60 petawatts annually. So this figure, I think, is thousands of times our energy use needed for our Earth. Okay, it's I think thousands of times already. We still remember the cooling capacity and also the heat capacity from the sun. This one is also thousands of times for more energy than the needed energy use by our Earth. So look at how. One example, is for the water cycle. Last time we know, oh, okay, so the snowy mountains, the snow will melt, and so then with the potential energy, right? We remember is the make use of the energy from the water it hold is hydropower. So they're using the turbine, okay, to convert the potential energy and the mechanical energy into electricity. So now I would like to talk more about another application. Maybe you have the chance to apply them in your projects. So it is water. This is a liquid state and solid state. And if they vaporize into water vapor, it will absorb heat. And from water vapor condense to liquid, it will release heat. Okay, so for this process, it will absorb heat. For this process, it reject heat. So therefore, we can see the water evaporation and condensation also very important for Earth's energy balance. It acts like a planetary heat pump by absorbing heat for vaporization and then releasing it at higher altitudes, okay, during condensation in the form of rain, in the form of snow. Therefore, it can transport energy from the tropics toward the poles and cooling the surface, which maintains stable global temperatures. The water cycle moves heat, moderates the climate, and prevents the Earth from continuously heating up by balancing incoming solar energy with outgoing thermal radiation. We can make use of the water evaporation and condensation. Sure, there's another one technology to make use of the energy from water is the water droplet. Okay, so they are using special surface. Okay, special surface. This surface can separate the charge. Okay, for raindrops, water drops, it produces electrical charges as water moves through a special surface. Okay, then we can see water can light up 100 LED lights. Okay, so we can see there's different forms to make use of the energy held by the water. Not only potential energy, but during the phase changes, evaporation and condensation, and also sure to release its charges through some surface materials. Okay. So now we understand in the future, we have many ways to make use of them. Then, so to go quick. Then I summarize for our general practice is when the passive design is to make use of the above natural resources like solar energy, the daylight, like the coldness of the universe, the wind, the natural wind, and also even the water. Okay, their cycle. Okay, the water cycle, evaporation, and condensation. And sure, we sometimes we have to design active design, air conditioning system, mechanical ventilation system, artificial lighting system to create the comfortable required built environment. Sometimes we combine them together, which is called hybrid system. Okay, with a passive and active combined way. So here I provided some material examples of the building passive design. Okay, so they consider the sun position, okay, the shading, okay, the materials, high insulation materials to prevent heat transfer, and also consider the natural ventilation to the air movement. The vent will remove the heat and also the pollutants generated in the built environment. And based on the make use of the design to create a air movement route. Okay, and also there's the plant more plants and greenery, okay, which we can use to absorb heat. And there are many concepts to make use of the. So here are the mature technologies. So I think I will not share details because I think during your undergraduate study, maybe you are familiar with them for the passive design. And the passive design, we can see we can even consider the microclimate, including to achieve the optimized building orientations and extreme obstructions. And yeah, consider the massing, the shading, the optical properties of the building envelope, and also consider the mass transfer between outdoor environment, indoor environment, and which is called infiltration, exfiltration, etc. And then, so for the, I think I'll leave this to tutorial session. Okay, due to time. Okay. And this, I think I will leave to later. Okay, this one together tutorial session. So this is consider the building envelope. So the optical properties thermal performances of our building envelope. That is means, so the material, if it's get hotter or cooler under the sunshine, that's for building envelope. The optical properties, the absorptance and emissivity. So for details, I think during tutorial session. And sure, for building envelope, not only we consider the optical properties, if it absorb heat or reject heat or emit heat. So we have many options. So not only the thermal insulation material, but also to make our building envelope to be adaptive. So including we are using phase change materials. So do we remember? So the strategy is a source, grid, user, and storage. So we can use phase change material okay, to shift and reduce the peak load of heating, cooling, and utility grid capacity. And it also can help stabilize the heat load and match heat. The phase change material as a thermal storage material, thermal storage to storage heat, to shift and to reduce the peak. So we can see the peak without, so the peak, lower the peak, and also shift the peak, okay, to other time. So through phase change material storage technology. And also, just like the previously we mentioned, like the plants can trace the sun. So we are thinking about if we can also make use of good of our natural resources for our building to lower its energy use. Yeah, the answer is yes. Okay, we do have some dynamic adaptive this AL Baja Towers, they can have, we can see they have 10 dynamic strategies, okay, to control the sun, okay, directions, etc., to make their envelope dynamic. Okay, so I think this is very common, especially in Germany, because the last time I visited one university in Germany, they just using glass as the building, glass and steel structure as the main structure. They using like the curtains, okay, to the whole curtains. Okay, so sometimes it's all transparent. You just like in outside, but for different seasons, they have different, okay, different strategies, different mode of their facade design. And sure, even not only you can change mechanical, okay, dynamic, but you even can change the colors, just like the chameleons. Okay, I asked someone some question. So why this animal change color? What's your hungry or finding mate, finding girlfriend, wife?
Just due to the environmental change.
Environment change. Okay, I think it's complicated. Some it's emotions and climate changes. Okay, before we think of the change colors to finding mate, girlfriend, boyfriend. Okay, so that's mainly due to the environment and sometimes also the emotions. Okay, we can do the same. Okay, we can also when we are happy, we make it also colorful. Okay, changing. Can you see the mood? Okay, the even the windows, the colors. I think for different directions, we can also change it. So and sure, if as a building energy designer, so if we design the passive architecture design, you want to know what are the strategies will fit your project. So this is a rough example for public housing. Okay, so public rental housing provides accommodations for over 30% of the local residents. And we did some researches. So we studied the different passive design strategies, how they will affect the energy use. Okay, for example, for this one, this example, so we found this is the solar window, solar heat gain coefficient is the most important. So the selection of energy efficiency glazing window is almost the first, and also the window to way ratio is very important for the building energy use for our buildings. It's how much solar energy will be introduced into the space. So comes first, solar heat gain coefficient, and the second, window to glass ratio. Window to glass ratio. That means so the ratio of the window areas so, and the third, these two are for windows. The third is if there is shading or not. Okay, shading or overhang. So because these are just to let you know, we have a method strategies. We can identify the best practice for your building. Okay, so that's for that. So for hybrid design is the combined together with the active and passive. So heat recovery technology is very popular because there's lots of waste heat from our power plants, from our industry processes. There's lots of waste heat. So make use of waste heat is very important. And also, even our air conditioning system, central, is a heat recovery system because, for the supply air for this room, 80% is the recycled return air of this room. Because this room, the air in summer is cold. Okay, we keep them. Okay, all fresh air air conditioning system will very energy demanding. Okay, so usually we just replace 20% of the supply air. So we try to make use of the return air. Is also a strategy of a heat recovery technology. And the solar thermal system, so that is easy to understand. So to convert solar energy, so solar thermal system, that's the thermal energy for swimming pool, for industrial processes, for power agriculture, for swimming pool, and for our shower, etc. Solar thermal energy, and also evaporative cooling. So evaporative cooling, it works on the principle of water evaporation through which the air is cooled down to a comfortable temperature. I also prepared a question, so a tutorial question. So we will together know more about is the evaporative cooling. This technology is to make use of the water evaporation. Okay, the energy the water hold for us. Okay. So through the simply we can see evaporative cooling is the water vaporized into vapor. This process will absorb large amount of heat to provide free cooling. Okay, there's applications. So we have also tutorial session. We have detailed discussion later, and sure, and ground coupled heat pump. So because we last week, I think we understand the efficiency, energy efficiency, our power plant energy efficiency for our air conditioner. So there's very related efficiency to the temperatures, the ambient air temperature. Because for heat pump, for air conditioner, so the outdoor air temperature will vary with the seasons. However, the underground soils, the underground, so the temperature always constant. So we can reject heat or absorb the heat from the ground. Okay, so then the temperature, we can lower the temperature and to achieve higher COP, much higher COP for energy efficiency. That is because we can see underground. So here is underground. Here is if it's lower than 75 meters, so it's totally constant, the ground temperature. So it will not be affected by the changes of our season. Also, active design, so also including not only for air conditioning, mechanical ventilation. So we talk about the energy efficiency sources, and also lighting and vertical transport and water systems. Even I think lighting, also contributes. I remember to around 7% of energy use. So now we also have the evolution of light bulbs. So because the first, I think I have, we also calculate the bulb energy efficiency. So during we talk about the energy efficiency, at the beginning, efficiency is really low, only 5% of energy converted into light. Okay. And so nowadays, so that's the reason why retrofitting strategies, so replacement with the lighting fixtures with LEDs, and is very that important for energy saving. So then after we still remember for building life cycle, so we the carbon emissions from its design stage, construction and operation and demolition. So building life cycle. So and now we talk more about AI empowered the technologies, how we can leverage the AI into our building energy efficiency. So the first So like the carbon reduction at the design stage, we can using the large language models and generative design tools to analyze our climate changes, climate adaptability, and microclimate to optimize the structural, layout. Okay, sorry for the typo. Layouts and propose energy harvesting, energy saving, and carbon reduction strategies. Okay, by using the leverage the LLMs, the large language models. Okay, to analyze our adaptivity and proposing. Then the second is the carbon control at the construction stage. So we should leverage the computing vision and VR, virtual reality, and other smart monitoring technique to analyze energy consumption and carbon emission to optimize the construction schedule and resource allocation. Sure, at the operation stage, we can leveraging the Internet of Things and the big data analysis of dynamic adjustments of building consumption and indoor environments, achieving high-level energy management. Sure, for the operation stage, we also repair and improvement, and so we also have different tools like a multi-model fusion technique, okay, to detect, and also I think it's and the drone now is very popular using the drone to detect the defaults, the failure of our buildings. Okay, so we have different AI empowered green building techniques across the life cycle for building energy efficiency, building energy transition. Okay, so sure, not only via design, we provide energy efficiency solutions. So, but we also have our strategies can be implemented with the ESG and also green financing. So I wish you have the chance, okay? Also work in that field to help us make money and also to achieve carbon neutrality. Okay, I think time's already over the planned time. So then we later, I think, come back after 10 minutes. We will have our tutorial discussion session. If you have any question that you think is difficult for you to understand, please come to me. As I have mentioned, because the first 2 weeks are end drop period, okay? I asked you to let all in, but they said for some programs, we have a mutual quota is 15. If you are belonging to that list, I think it's difficult if you are from other programs, okay, with limited quota agreement. And also for some part-time students, if they think you have opportunities to select this subject next year, okay, maybe they will not get you in. If you do really, for part-time students, if you do really want to be ended into this course, please write to me. Yeah. Okay, thank you. Had 10 minutes break. Okay. Thank you. Hello. Welcome back. In fact, today we mainly talk about carbon emissions and carbon peaking, carbon neutrality, and sure. So, how to achieve energy efficient buildings. So, through passive design, active design, and how to empower leverage the AI, okay, into our building energy efficiency technologies. So then we merely understand for outdoor carbon dioxide concentration levels. So we understand for outdoor concentration level, okay, the updated finger, I think is around, okay, this one. So this is for outdoor. Then we are curious about if we have any design criteria for the indoor carbon dioxide level. Okay, so indoor. Do we have any requirements for the concentration levels of carbon dioxide for our indoor environment? And do we have any strategy? Okay, is it has any linkage with our air conditioning different control strategy? Okay, so yeah, the answer is yes. Okay, I will. Okay, I think I will upload it. Okay, online through Blackboard. Don't take a photo of me. And so so typical indoor carbon dioxide concentration levels is around a range around 400 ppm. That is merely similar to our outdoor air, and to 1000 ppm in the occupied spaces. So levels above 1000 ppm may indicate inadequate ventilation and can affect the occupant comfort and cognitive performance. So if there is any linkage with our air conditioning system, the answer is yes. So for the demand controlled ventilation system, okay, at a full occupant, okay, with a carbon dioxide sensor, okay, with the full occupant, yeah, it's like design outdoor air, okay, flow rate into the space. So by monitoring the indoor carbon dioxide concentration levels, so the demand controlled ventilation system can adjust the amount of fresh air supplied to the space and optimize air conditioning demand. And what about when carbon dioxide concentration levels rise due to the increased occupancy, the system increases ventilation. Not only ventilation, but it's the supply outdoor fresh outdoor air. Okay, so the amount of outdoor air to maintain air quality. So, and if the occupancy is low and the carbon dioxide levels drop, ventilation rates can be reduced. okay, can be reduced at a partial occupancy. So this is also another common energy saving demand controlled air conditioning system. So this approach can help us balance indoor air quality with energy efficiency in building air conditioning system. As we know, for the built environment, we have to consider the temperature, the humidity, the temperature, and also the carbon dioxide concentration levels. Okay, maybe we can watch the video to know more about demand. Demand control ventilation. So know more about this control strategy related to carbon dioxide. Okay, and now we understand the importance of carbon emissions, not only the carbon emissions in the atmosphere, but for our built environment, for our indoor environment. We also can design our ventilation air conditioning system to demand controlled system for so there I think 5 benefits or 6 benefits from the video. Not only for improved indoor air quality, but also for building energy efficiency and lower energy use for our ventilation system, air conditioning system. So that is understand the carbon dioxide levels in the atmosphere and also for our built environment. Then the second question is I just also introduced about the evaporative cooling. Now let's know more about evaporative cooling. The first is to understand the specific enthalpy of vaporization and its applications. So regarding this one, so we know first we want to know, some of you may be not familiar with it. So now let's know what is specific enthalpy of vaporization. It is also called latent heat of vaporization. Is the amount of energy required to convert a unit mass of liquid into vapor at a constant temperature and pressure. What's this value? So we can get it from the water steam tables and also the diagram, the pressure enthalpy and temperature entropy diagram. So at the standard atmospheric pressure, this value is 1 kilogram water vaporized into water vapor at the same temperature. It will absorb 2,260 kilojoule heat from its surrounding. So this absorption process can provide cooling. Okay, so for example, the evaporative cooling can average the high enthalpy of vaporization of water. So when water evaporates, it absorbs a significant amount of heat from its surroundings, results in a cooling effect. So one common example is the cooling tower. The cooling tower not only for heat rejection, so they are using the water holding the heat, and release the heat. So when it's vaporized, so this is for power plant, the cooling tower. We are using water and water vapor to release the heat, waste heat from the power plants. And even for our air conditioner, we have a cooling tower. We are using cooling water. Cooling tower condensing cooling water. To carry the heat and release the heat into our environment and air, mainly through the evaporation evaporation of water. And sure, there is direct evaporative cooling coolers in dry climates. Yeah, one simple is just using the water, and so an example is after shower, you feel chilly. That is because the water on your skin vaporizes into water, it will absorb heat. So this is a direct evaporative coolings, which can be widely used in dry climates. I think in Hong Kong, sometimes we have such evaporative I think it's indirect evaporative cooling for some, I think a sports center without air conditioning. They are using such evaporative cooler, and even there's indirect evaporative cooling. I think we have in our department we have a professor working on this. It's the same, just like the cooling coil. You there's sprinkling water and the water vaporize can cool down the hot air. So then previously we also have the example, I think, here, the evaporative cooler, so using the water vaporize into water to cool down the air. To cool down the air. There is evaporative cooler. There is a direct one from dry regions and also indirect one. So what's the meaning of indirect? Indirect is there is no direct contact between the hot air and water. Direct evaporative cooling is the direct contact. Okay, and so in the future, maybe you can also make use of the cooling, heating power from the water, okay? And sure, there's other applications. So for the vaporization, and specific anti-vaporization of refrigerants, so which also popular make use for our refrigeration system, air conditioning system. The refrigerants also vaporize condensed. So during that process, absorb heat and release heat. This is our indoor evaporator. Indoor unit of air conditioner is evaporator. So the refrigerants, the liquid state vaporize into vapor. Okay. So for our indoor unit evaporator, and outdoor is called condenser, is the vapor condensed. Then when it's condensed, it will release heat into our environment. So there is many applications of phase changes. Okay. Our water steam and refrigerants. That's what we have started for engineering thermodynamics. We understand the thermal properties of our fluid, okay? The working fluid. They can be, water, steam, and refrigerants for our air conditioning refrigeration system. Then the third is because we always mention about there is atmospheric window, we mention merely, if your thermal radiation with the spectra between 8 to 13 micrometer, so there is a window, water vapor and carbon dioxide will not absorb the heat. Okay, will let you leave and into the space. So what's the reason? Then I'll get an example for you. I ask you to do the simulation. Okay, so the thermal radiation spectrum. So, okay, I will let you know more about enthalpy because I prepared the one. So, enthalpy is very interesting. Although it's not with a long history, but it means heat. So enthalpy means heat. And if you have studied engineering thermodynamics, we know entropy. Entropy let us know the process direction. So the energy transformation, it will happen or not. Okay, or turning is entropy. Entropy uses meaning is energy transformation and the direction of the processes, and energy is the work. Okay, perform work, but enthalpy is heat. Means the heat. So enthalpy is very important. In fact, for our discipline, because enthalpy uses the root of a Greek word for heat. So then any changes of the enthalpy of the working fluid means it will absorb heat or release heat, or if conduct work or receive work. Okay, so enthalpy is very, very important, especially for our major. Then to understand the thermal radiation, so our buildings, you and me, we will radiate, okay, heat into our surrounding. So how to calculate? Here is the equation. If it has a specific continuous spectrum wavelength, and then I want to do the calculation is using this calculator. Okay, then I remember I asked you to calculate. So if the temperature is 10 and 40 degrees Celsius, because I let you understand 10 is winter, 40 degree maybe summer, some surfaces with 40 degree. So they will shift, okay, they will shift. But I think through, let's calculate one. So demo one calculation. Here we convert the calculation, the black body calculator. Oh yeah, this is for black body. Okay, if we set, okay, the cut-in wavelength 1, so cut off is 30. That's for the for should we, and also if the I think I using, if 10 degrees Celsius is we are using 40 degrees Celsius, then is okay. Then this is a 40 degrees Celsius. If we assume thermal emissivity is 1, then we do the calculation. And we got the spectral radiation. This is for a black body with a temperature of 40 degrees Celsius. This is the temperature of object around us, okay? So let's look at the spectrum radiation. It's what about its peak? Intensity peak. Intensity peak here provide us is 11.7 micrometer. Is so we can see the peak with the wavelength. Okay. So if the black body is 40 degrees Celsius, so the peak intensity, the wavelength is, do we remember I always mention if you are with the wavelength, thermal radiation wavelength between the 8 to 30 micrometer, the greenhouse gases will not absorb. Okay, so that's called atmospheric window. Okay, previously, so we can see the peak intensity is 11.7 degree 7 micrometer. Yeah, this is for and then what about the other one? Okay. This is for cooler winter. Okay, our outdoor now is maybe it's 10 degrees Celsius. Let's see the results. Okay, the peak wavelength is 9 point, it shift, okay? With the peak intensity of thermal radiation is, sorry, cannot remember. Can you see? Usually, for our Earth temperature, although with the changes, our thermal radiation with the wavelength mainly, okay, in the atmospheric window. But what's the reality? The reality is almost all subjects with low thermal emissivity in this range. You can check for glass. Although we think glass, you check glass thermal emissivity is high, but definitely, so with between 8 to 13 is very low thermal emissivity. So that means our glass doesn't know how to release heat into our space. Okay, so the glass, although it's transparent, is always very hot. Okay, and the sunshine is very hot as well. So now we understand, so the thermal radiation spectrum of the black body objects with the temperatures, although it shifts, but it's the peak is mainly in the atmospheric window. So this is for the emissivity subject with the thermal emissivity 0.1. Unfortunately, most building materials with low thermal emissivity, especially from 8 to 13 micrometer. Okay, wait a minute. So this one, I think you can got more. So even not only so for different temperatures, okay, with the not only the spectra, okay, will shift, but the intensity will vary largely. Okay, so high temperature, high energy, spectral energy density. Okay, lower temperature, so much lower energy intensity. And then I think that's okay. That's lastly the fourth question is about the solar reflect index. I think I didn't mention much about it. Then now we go back to this example. So regarding the, so I think during class I mentioned the infinity energy from the sun, the energy from the sun, the cooling energy from the universe, and also the energy held by the wind and by the water, mainly due to its potential level, potential energy, and also vaporization. We measure about passive design for our building envelope. Okay, we have strategies. We consider its orientation, massing, shading, material selection, thermal mass, the thermal insulation, etc. However, I mainly introduce about its the optical, the solar performance. So the thermal, then I have to introduce the solar reflect index. So the solar reflectance index indicates the constructed surface ability to reject solar heat, and is the combined value of reflectance. Okay, how much solar you will reflect. And there's another one, because we remember the cold universe, right? So we want to know its thermal emissivity. So because all objects will radiate long wave infrared light, so then this is the combined effect of reflectance and thermal emissivity. So for solar reflect index, it's defined as a standard black is 0. Standard black is 0, means with a low reflectance, high emittance, and standard white is 100 reflectance and emittance. Then I want to know, you think solar reflectance higher, cooler, or lower, cooler? Lower cooler? Lower is black about standard black. Huh? What do you think? You think solar reflectance, this value is lower, so the surface will be cooler under the sun? Or higher, cooler. Lower, you mean solar reflect? So with solar reflect index 0 for standard black, definitely it's real hot or warm. So therefore, if in Hong Kong you want to keep our building cooler, the surface cooler, we should choose materials with a high solar reflect index. High solar reflect index. Okay? Higher the cooler. So the first we have to understand is if you want to cooler, okay? If you expect a cooler surface, okay, a cooler surface, then the solar reflect index, this value has to be higher. Okay? The higher, the cooler of the surface exposed to the sun. However, I very unluckily, all building materials, all construction materials are featured by low solar reflect index. Okay? If you think it's difficult to understand, not only concrete, it's terrible. Under the sun, it's over 70, 80 degrees Celsius. Even now, in the afternoon, they can be over 50 degrees Celsius. Oh, another story is metal. Metal is even worse. Why? Because metal with low absorbance of solar, but it has almost zero emissivity. All heat it will trap. It doesn't know how to radiate heat into its surrounding. That's the feature of metal. Also, like so we're using silver, right? The low thermal emissivity to keep heat. So all metals with relatively low absorbance, higher reflectance, but really low emissivity. And not so for concrete, for metal, even marble, white marble, light marbles, like wood, okay, all materials, all pavement materials, all are very low solar reflect index. That's the reason even very light marble, you still very hot. This is very important. So luckily, almost all common building materials are featured by low solar. So therefore, under the sunshine, their surface temperature can be really high. So that's the story about melted road. Okay, so we see the road, and just like a chocolate, melt like a chocolate, even runway melted. Okay, so and then you want to know about, in fact, Beam Plus, we start to have this solar reflect index. Here. So for Beam Plus, they recommend for the roof, green roof materials. Okay, sustainable building design is the solar reflect index is 78 or above, 78. Okay, it means a cooler roof, a cooler roof. So here I also provide you an example. Okay, understand concrete. You take an example, concrete tile as an example with albedo reflectance of 25% and emittance of 90%. Let's do the calculation. And through the calculator, we understand the solar reflectance index, the importance. Let us know under the standard conditions show the importance of solar reflectance index. So we remember for the concrete take an example of the concrete. I remember the reflectance is 25%, right? Thermal emittance is 0.9. Then this is for concrete tile. Okay, we got the figure from the table, right? So then we calculate the solar reflect index. So what's the value? Sure, the solar reflect index will affected by the wind velocity, okay? Because wind is a good, ventilator to remove heat. So what's the value at low wind? So the solar reflect index of the concrete tile from the table is 23.9. Okay, this means it's low. Okay, then let's see for the standard test condition I given in the PPT file. Can you see what about the is a sample the surface temperature if it's opposed to 1000 watt per square meter sum? What about the surface temperature? Okay, maybe if you think difficult, can you see the calculation? If no wind, is surface temperature over 90 degrees Celsius. Okay, now you know the importance of solar reflect index. Then what about black surface? Black surface even worse. Okay, here can be over 104 degrees Celsius. Okay, but this is there's a condition later we will discuss. It's a very strong solar irradiance and also where it's hot. Okay, it's hot, is 30 something degrees Celsius. Okay, and also very, very low wind. What about wide surface temperature is around 50 degrees Celsius. Okay, so we can see if a concrete tile for that test conditions, its surface temperature can be around 90 degrees Celsius. So that's the reason we can understand. Maybe there is a convection heat transfer around us, but you see in summer, we measured the roof temperature of our buildings is really almost 75 to 80 degrees Celsius. Okay, so for some materials with the low solar reflectance index. So I think you can do the calculation. However, I have mentioned, so this calculator, they have the strict specification following the ASTM E1980 specification, including for the solar irradiance and the ambient air temperature is also high, is 37 degree around, so it's considered. So there you can use this calculator to calculate this example, these two example. So that's not maybe not that accurate, but definitely it can provide us, okay, to help us to understand the importance of the solar reflect index. Okay, let's see the example. So the first example is for concrete is absorbance, then its reflectance is 0.25 reflectance. This is reflectance. And emissivity is 0.9. This is for concrete. I think we just did the calculation. And then copper. Then for copper. So copper are checked. Its absorbance is only 25%. Okay, but for concrete, high absorption, right? So copper is he knows how to reflect solar irradiance, but it's we can see it's without any treatment. Okay, its thermal emissivity is only 0.03. That's the finger. That's why outdoor copper pipe also very hot. Okay, then how hot it is? Let's check. Okay. he knows how to reflect heat, but here is really low, the thermal emittance. Okay, then we calculate. Okay, it's the same. Okay, it's the same. We can see the solar reflecting index of the copper is around 30 to 40. And under the strong sunshine, although he knows how to reflect the solar energy, but the surface temperature, the sample surface temperature is still hot, like 84. So the concrete, the metals, the main building construction materials, they absorb or trap heat, okay, for our outdoor environment. So therefore, consider this for the building construction. If the city, okay, cooler surface and hotter surface, there will be another story, okay? Because it accelerates the heat island, urban heat island effect. Not only the heat rejected from our air conditioning system, from our car, and from our energy utilization processes, because all losses becomes heat. But also, in nature, we didn't make use of the good use of solar energy and the cold universe, okay? So that's causing the urban heat island effect and high building energy use as well. So you can calculate. So we don't have assignment, and however, so all the taught materials, maybe they will be in our examination papers, okay? So I wish you also, we together, we have some discussions to does this change your views? Does it change your views on the urban sea temperature? No? Okay, so this is the end of our tutorial session. I will upload through Blackboard this version, okay? This version after tutorial session. Okay, maybe it's time and see if you have any question. Okay, this week is end drop period. If you want to drop your subject, please do it quick, okay? Because we want to release places for other students. For the glass is another story. If you don't consider the transmission of the sunlight is the same, okay, same story. But it's also there's glass can transmit solar irradiance. It will also absorb. It also release. Okay, it becomes complicated. Okay, thank you for your good question. Okay.